So last time we were just finishing discussing this problem about weighted intervals. I'm not going to define the problem again, or the recurrence. The recurrence is up here. Just remember, though, that opt_j, what that means this is the optimal solution that can be obtained when you consider the intervals numbered 1 through j, and they're numbered according to an ordering of their endpoints. Okay, their finish times. And so this was the recurrence, and then we argued last time that we could look at this as a recursive program, but that would be inefficient, or we could add on the memoization idea, and that would improve the efficiency, or we could ultimately look at this as dynamic programming, which meant you did a bottom-up evaluation or a bottom-up solution of the recurrences. So on the next homework, I'm using this term, solving the recurrences. What that means is finding a value for the function that's being defined by the recurrence. So in this case, it's opt_j. So solving the recurrences means how do you get a value for opt_j for each of the j's. Okay, and in the dynamic programming approach for this, first of all, you just set opt0, for example, to 0. That's the base case. And then for j equals 1 to n, there are n of these intervals. You can just say, well, you just use this recurrence, because the point is that when you want to evaluate what opt_j is, when you want to find its value, the recurrence says you need to have opt_j minus 1, and you need to have opt of pj. But pj is always less than j, so if you are evaluating the opt function in this order from j equals 1 to n, then it's fine. You have available to you what you need whenever you want to evaluate the value or get the value of opt_j. Okay, so that's dynamic programming, and it's clear that this has n iterations because we're going from 1 to n, and it's clear that in evaluating any given j, we're just doing a constant amount of work because you have to look up this, you have to figure out what that is, but that's already pre-computed when you did your sorting. You have to then look up opt_pj, you add vj to that, you do this comparison, and you're done. And that gives you what opt of j is. So that's just a constant amount of work per j. And then you have n values of j, and so that means this is theta n time. Okay, so that's almost where we ended. We ended very quickly talking about traceback, and that's where I want to start today. Because this computation here just gives you a value. It gives you opt of j for each j. It gives you a number. But it doesn't actually tell you what the selection of intervals should be. What is the optimal selection of intervals? And so for that, we wrote up something. I forgot my notes today, so I only have this piece of chalk between me and you. Okay, so I'm not defending myself with a set of notes today. Okay, so how did this go? We said something like first of all, if j equals 0, okay, so we had find sol of j. We want to find the solution, the set of intervals that you're going to use, you're going to select between the intervals 1 through j. If j is 0, just return. You don't have to say anything. Okay? Else, well, j is not 0. That's when you want to figure out, are you going to use interval j or you're not? Okay? Well, what determines whether you're going to use interval j? If opt of pj plus vj, if that's greater or equal to opt of j minus 1, then output j and recurse on find sol pj. Okay, so this is saying, yeah, it's better to take interval j than not to take interval j. This is what you get if you don't take interval j, and this is what you get if you do take interval j. Okay, so if this is better than this, although I have the possibility of equal, I'm just breaking ties that way, then you want to output j, because the solution should be outputting intervals, and then you recurse on what should you do on the intervals between 1 and pj. You know that if you use j, you can't use any of the intervals past pj to the left of j. Okay, else if, and then this else, we output, no, here you just recurse. You don't know what to output yet. You recurse on find sol of j minus 1. Okay? You're not using interval j, so you can use anything between interval 1 and j minus 1. You don't necessarily know that you're going to use interval j minus 1. That's why you don't output anything here, but you recurse on that. Okay. Now, everybody see that this is right? I mean, it's just using the logic of the recurrences backwards now. We use it forwards to get the value, and we use it backwards to get the actual selection. Now, when we're doing this computation, we already know what these values are, because those have been computed in the forward during the forward computation, and they're in a table. They're in a table called opt, so you can just look these up. So what is the running time of this algorithm? Well, actually, the forward time was theta n, but the backward is also theta n, but maybe for a slightly easier reason, or maybe it's a more complicated reason. Maybe it's harder to see what's going on here. The point is, you're just chasing pointers. In a sense, you're chasing pointers. You're yeah, why is it order n? It's supposed to be easier to see. Anybody see it? Yeah.
Well, at each time you run it, you're either calling it again with j minus 1 or calling it again with p of j, which is less than j minus 1.
Yeah, okay, sorry. Yeah, you're right. You're absolutely right. Why I paused here is I thought we were going to branch two ways, and then it started spooking me. But, in fact, you only branch one way. You only recurse one way. So on each j, either you return, okay, that's fine, or you're going to recurse on find sol pj, and pj is less than j, so those are always decreasing. Or you're going to recurse on find sol j minus 1, which is also less than j. So for every time you enter this, you're going to recurse on some value find sol with a parameter smaller than j. And so these things always just decline, and you can't go lower than 0. And so certainly, and you started at n. Initially, you call this with find sol of n, because that's the full set of intervals. And so this is just also just takes theta n time. Actually, all we've established is it takes big O of n time. If I wanted to show that this took theta n time, what would I have to do in addition? See, this takes big O of n because I just argued that at most it's going to make n recursive calls, and the amount of work you do at each recursive call is constant. So it's bounded by big O of n. To say that it's theta n, in worst case, means that actually sometimes it really does take a number of calls that are proportional to n. So in order to get that, I'd have to find an example, or one way to do it is to come up with some actual example or class of examples that are parameterized by n that each take a time that's proportional to n. And then that would establish theta n. Yeah?
There is where all intervals are non-overlapping and they associate each other.
Oh, so you're suggesting that one of those would be where all the intervals are non-overlapping? Yeah, maybe. Oh, good homework question. Anyway, I just wanted to point out what's the difference here between concluding that it's big O of n and being able to conclude that it's theta of n. Whereas over here, we concluded that it was theta of n and not just big O of n. Why could we say it's theta of n over here? This is a more precise result. Theta of n is more precise than big O of n. And why? It's bounded from below as well. Why?
Because in order to have something be big theta, then it also has to be big omega.
Right. Now you're talking about the definition of theta, but how do you see in here that the work is actually bounded below by n? Anybody? Anybody else? Yeah. All right.
We're running an iteration.
Yeah, you're running iterations here. This is for j equals 1 to n. There's nothing is problem dependent here. It's going to run n times. Okay, it's right there in there. Whereas here, it really depends on what gets evaluated. You start out with find sol n, and depending on what happens here, your next recursion could go well below j minus 1, and so you could have problem data where this just zips through in less than n iterations, much less. So we can only, at that point, conclude it's big O of n and not conclude that it's theta of n until we have an example in a class of examples that really take something proportional to n time. Okay, this is a real fine point, but it's the kind of fine point that comes up, that's good to come up on exams. Okay. All right, so that's the traceback. That's one version of the traceback, and this is the traceback that's in the book. Now, I don't like this style of traceback myself because you're actually doing comparisons, things that are similar to what you were doing in the forward evaluation of the recurrences. And if you just leave pointers when you're going forward, you don't even need to do these comparisons. So these comparisons are really unnecessary and redundant. And here's what I mean by that. Suppose when we build the opt table, here we are at j. This is during the forward computation. This is when we're doing these n iterations. And so we're evaluating what opt j is. And when I'm looking at j, okay, how am I figuring out what opt j is? Well, I'm applying this recurrence, okay? So right here, I'm comparing opt j minus 1 and opt pj plus vj, okay? And I'm finding out which of these is I did this right. Max and greater than or equal. For a moment, I thought it was I'd gotten this sign there wrong. Okay, and here we're comparing these two terms, right? And so we know at this moment whether opt pj plus vj is greater than or equal to this. Why later in the traceback should we do that comparison again? That's wasted. That seems silly. All we need to do is just record it. Okay, and how are we going to record it? Well, you record that with a pointer. So from j, I'm going to either have a pointer to j minus 1, or I'm going to have a pointer to pj, and not to both. So when will I leave a pointer to j minus 1? Well, if you can see where I'm going with this, you'll be able to answer that question, but you may not see the big picture yet. Okay, yeah. Yeah, when the max of these two terms is opt of j minus 1, then I'll leave the pointer from j to j minus 1, like that. And when the opt of pj plus vj is bigger than the opt of j minus 1, then I'll leave this pointer. Okay? So one or the other pointers is going to be left depending on what the situation is. Of course, there could be ties. And here I've broken the tie in favor of pj. That's because it gets me further to the end faster. It'd just be faster computation that way. Okay, so if I've left these pointers, so everybody now has a pointer from them somewhere, because this is from j equals 1 through n. So every j is being examined, and we're going to leave a pointer from each position. Now here's n. It has a pointer. So when I do the forward computations, I leave these pointers. Now, how do I find the actual set? How do I do the traceback to find the actual set of intervals that gives you the optimal solution? Anybody? Yeah.
You just follow the pointers back.
You just follow pointers. Just from j, from n, you follow its pointer. And from its pointer, you follow its pointer. And from its pointer, you follow its pointer. And from its to, until you hit back to 0 or 1. And the cells that you went through when you follow the pointers, that selects, that identifies a set of intervals which is an optimal solution. And to see that that's right, well, you can see it in one of two or many ways. You could just say, well, this pointer business is just implementing this. We already argued that this was right. We saw that this was right. All the pointers business is doing is saving us these comparisons. So following pointers back is exactly what this is doing, which is another way, by the way, of sort of graphically seeing that the time for that is, again, order n, because these pointers are going to the left. So that's one way to say that this is the right thing to do. Or the other is kind of to bring in again the meaning of the recurrences, which is to say we're interested in opt n. What's the optimal solution when you can consider intervals from 1 to n? And the fact that this pointer is here means that there is an optimal solution where you take n. I mean, this is a pointer that's not to n minus 1. So this means, yes, you're going to take well, actually, yeah, you needed. It's not just enough to chase pointers. You also have to interpret them. When you, you have to interpret what they mean. If the pointer goes just to its neighbor, then you're not actually going to take that interval that's associated with that cell. But if it goes beyond the pointer, if it goes beyond that, no, I'm making a mistake. Who can catch it? Who's seen what mistake I've made? Okay, I was just saying it's not enough just to chase the pointers. It is true that when you chase the pointers, you'll figure out what the intervals are that you should take. But how you do that is what I've messed up. Okay, and let's just look at n here. Well, I'm not having a good hair day. I missed my bus this morning, and then a number of things. Forgot my notes. Okay, so but anyway, from here is n, and let's say its pointer goes to n minus 1. Okay, do we take interval n or not? Who says no? Why?
So we choose opt to n j minus 1.
Okay, it looks like that the opt of j is equal to the opt of j minus 1. I mean, sorry, opt of n is equal to the opt of n minus 1, so we shouldn't take it. But what if p of n is equal to n minus 1? Then do we take it or not? Okay, so I guess I should have, the easier case would have been, what if the pointer goes way over here to something less than n minus 1? Then I think you'd all say, yes, you definitely take n, okay? Right? Because you definitely, you're in the case where the opt was this thing. Okay, because p of n is less than n minus 1. The confusing case is this one, when p of n, when n goes to n minus 1, it might have been that this was the winning case, and this is strictly bigger than this, okay? Or it could have been that pj is equal to n minus, or pn is equal to n minus 1, right? In which case we should take n. Yeah?
pj to be right next to pn.
Oh, okay. All right, so this is a double twist. This is like, the extra twist after you think that the last twists in the movies happened. Okay, let me just explain the one before that for a moment. Okay, so the issue that I'm concerned about here is that maybe this here, where you go from n to n minus 1, was actually the case of this case. But it just happens to be that p of n is equal to n minus 1. Okay. Then the solution certainly that you can do is just remember this. Just note, was this p of n that you're pointing to or not? Are you pointing to p of n, or are you pointing to just n minus 1? So if you're pointing to something beyond n minus 1 or j minus 1 in general, you don't need to note anything. But if you're pointing to your neighbor, then you just note whether this is which case this was. And then when you do the trace back, then it's very clear. It just tells you if you're pointing to your neighbor and you don't have that mark, then you don't take the interval that you're pointing from. Okay. That's fine, that works, but it's not this extra thing is not necessary, and the comment was made, why so? Yeah?
I was just wondering if you could get away with only having that note and not having like the pointers.
Yes, you could do that too, because so the comment was maybe if the optimal is your neighbor, you don't even need a pointer. Okay, just have a pointer if the optimal is not your neighbor. It goes to pj. So if you're sitting at a node j and there's no pointer from it at all, you know that the optimal was j minus 1, and that could also serve to note that you should not take interval j. That's true too. So that sort of saves on the pointers and also encodes what the solution is. Okay. Getting back to an earlier comment was that I don't need this p of n. I don't need to mark which one of these. I don't need this additional marking because the way I set this up here with the possibility of equal here means that you're only going to go to your neighbor, you're only going to point to your neighbor if your neighbor is strictly better than the p of j case. So if you point to your neighbor, it's because no, I'm getting confused about your comment. Let me live with this one. This is right, and there may be fine tweaks that we can do to even make it better. But this one's fine. We're just going to record whether what the meaning of that pointer was. And then you can chase pointers and get the intervals. This sounds like a great homework question for today, for this, which is to write this up better than I just said it. Okay? Write it up in a way that makes sense to you. And so this trace back, not this way, this is what's in the book, but write it up chasing pointers. And therefore, anybody who's not actually here now, when they see that on the homework, they'll have to watch the video. Okay. All right, so that's trace back. And I usually like the pointer approach or the breadcrumb approach to traceback, as opposed to this kind of approach, which is doing some redundant work. Yeah, question?
When we run the original talk,
Yeah.
why can't we just record which J's we actually go through and then output those values? Because then you wouldn't even need the pointers for it to go
Right.
through it all over again. You just, once you pick a J, you just put it in a separate array and then you output the whole thing.
Right. This is the classic question that's always asked when people first learn dynamic programming, which is, why can't we accumulate what the optimal solution is as you go forward, as you do the forward computation, as you do this? Why do we need a traceback at all, anyway? Okay? And the answer is, you really do need the traceback. You really can't know, as you're going forward, which of the intervals are ultimately going to be in the best solution. So the best way to convince yourself of that is to just try to find an example of that, where as you're going forward, you have a particular interval that really looks good, but because you take it, or if you say at that moment that you're going to take that into this solution that you're going to use, then that will cause conflicts with other things that you could have done later that were even better. Okay, so yeah, you need the traceback, and this is what distinguishes, one of the things that distinguishes dynamic programming from greedy algorithms. In greedy algorithms, we always had a myopic approach, where as you were going through the data and the problem, you could decide what to do, and that decision was good enough. I mean, it could stay. Here, you can't in problems that are, typically in problems that are solved by dynamic programming. So this will again be a homework question. Need the traceback to find an optimal solution. And we'll see this over and over again in dynamic programming problems. It's a standard feature of problems that are solved by dynamic programming. Okay. All right, so that's dynamic programming in all of its gory detail for this interval problem. Now I'm going to do another dynamic programming problem. Actually, we're going to do two more in this class, but today only one, and one more. And then on your homework, you'll see some additional problems, homeworks. So the next one is a fairly realistic problem that comes up in computational biology, a little bit simplified in comparison to the versions that people actually solve, but pretty realistic for the way they solved it like 20 years ago. So this is called RNA folding, or the book actually calls this RNA secondary structure. And this is in the book. I think it may be immediately after the interval problem, but if not, no, it's between the interval problem and RNA folding. I think there was another topic that we're skipping. So in RNA folding, you have an RNA sequence. RNA sequence is just a sequence on 4 characters, 4 types of characters. A, U, C, and G. And so it's just some string, it could be quite long, that's composed of these characters. So A, U, U, C, G, C, A, U, C, G, A, U, C, G. Yeah, whatever. A, U, okay. So this is an example of an RNA sequence. This one will be very short. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. What's the smallest RNA sequence of interest? That's a question to see if anybody's taken a molecular biology course recently. Yeah. What? I heard a number. What was it? I heard your hand went up, didn't you? 4? No, not that I know of. Maybe. 21. Anyway, complete irrelevant comment about, but there are RNA sequences of length 21 that are very important, and the people who discovered them and figured out why they're important got a Nobel Prize a few years, just 3 or 4 years ago. At any rate, but RNA sequences can also be quite long. They could be in the several thousands of length, even like 15,000 or so. Okay, but the typical ones where this secondary structure issue comes up are in the hundreds. At any rate, we just can think of this as a sequence where the characters are taken from the alphabet A, U, C, G. Now, one of the confusing things about talking about these characters, so this is a character, G is a character, U is a character, that's just colloquial, normal use of the word character, and that shouldn't, hopefully nobody is confused by that. But in the world of molecular biology, these characters are also called base pairs, which is really unfortunate for us. Okay, because the word pair suggests there are 2 of them, when in fact we're only pointing at one of them. Okay, so the book will talk about base pairs, but they're really just talking about a single character. And again, anybody who has a class in molecular biology will be able to guess where the origin of base pair comes from when you're actually only talking about a single character. Anybody know? No. Yeah. Yeah. There can be two strands that hybridize, and so whenever you're looking at a particular character, there's the complementary character, in this case A, if there were 2 strands. Okay, so this is a base pair, and each one of these is a base. But if you're only looking at a single sequence, you're just having a single character, so if you call that a base pair, it's kind of confusing. Okay, I'm only pointing it out because the book uses that term, and it might be a little confusing. Okay, so what are we interested in? We're interested in trying to figure out what is the folded structure of this sequence. And RNA sequences, individual sequences, fold up in some 3-dimensional structure. It turns out that in RNA, you can learn a lot just by looking at what's called the secondary structure, which is how the folding looks on the plane. Not in 3 dimensions, but in 2 dimensions. So what it looks like typically, and the book has a nice picture of this, is, let me just draw one. I don't know. Okay, this is a cartoon, and the sequence is along in here. So here you may have an A, U, C, C, A, U, U, C, G, C, G, C, G, A, U, C, G, no, that's fine. C, G, elongate this a little bit. Okay, so what I'm drawing here, the sequence you're seeing along here by following the line. So this is a sequence A, U, C, C, A, U, etc. Okay? Oh, and I didn't put anything here. Okay. U, U, C, G, G, U, whatever. And these these pairs, not a base pair, this is a matched pair. This is a match, okay? So this is a match. And if you notice, whenever there's a match, it's always a C matching a G or an A matching a U. Okay? So C to G, A to U are permitted. So when you look at this, you see in here some matches. And now where the only things that are matches are C to G and A to U. Now, if you were to take this molecule, and it's written on, it's in two dimensions. It's just on the plane. If you actually look at this in 3 dimensions, you have some extra twists in there and folding back and so on. But on the plane, this is the 2-dimensional picture of its folding. It's folded back on itself. These are chemical bonds in here. Okay. If you now were to consider just taking these two ends and pulling them apart on a line, then, let me just see if I can write this. A-U-C-C-A, U-U-C-G, G-G, G, why did I make this so big? A, U-C-G, U-C-G, G-U. Oh, no. Where am I? Here? U-U-C-A-U. U-U-C-A-U. Boy, this will really make the people at home crazy. I've gone across two. Okay, is this right? Did I make a mistake? Oh, I'm just tracing this from here. Okay. All right, now let's look at where the matches are. The first A matched the last U. Okay. Then the second character U matched the next to last A. Okay. And then we had C matching G, C matching G. Okay, C matching. Oh, these G's, where are the G's? Right here? These?
Yeah, 4 G's next to each other.
Okay, 4 G's next to each other. And these were the middle two. Okay. C matching the middle two. G, nope. C matching G, C matching G. Okay. Then the next case, we have a G matching a C. Well, this C is 3 places from the end, right? And which G is it matching? Is it this one? No? This one? Okay. C matching G and C matching G, AU, AU, and those are neighbors. Okay, so I think I can do that one. AU, AU. Okay, there we go. Okay, so when you take the matching pairs that are in the 2-dimensional picture, and you take the molecule and you stretch it out on the line, what you see is that the matches are nested. They're non-overlapping. Okay, so the matched pairs are nested. That means non-overlapping, non-intersecting. Non-intersecting is a better term for that. We don't have this U, for example, matching with, well, it'd have to match with an A, but there's no A over there anyway. Here's a C, which is unmatched. Here's a G that's unmatched, right? So this G is not participating in a match, and this C is not participating in a match, right? So according to this rule, we can match up C and G, but if we did, that match would intersect other matches, okay? We don't have that. And what would that look like? I don't know. It would look messy over here if you had that in there. It would be weird. So what happens molecularly is you have a kind of folding back. You have you have the strand of RNA that folds back on itself in ways that make these kind of nested structures when you look at it this way. Okay, all that is to motivate the following problem. You're given an RNA string. RNA string. A matching is a set of disjoint pairs of positions, let's say I and J, where the character of I, where if, or maybe I'll just say such that, if the character at I is equal to U, then the character at J is equal to T, okay? If character of I equals C, character of J equals G, and conversely. There should be 4 cases here. Okay? Yeah. Yes, thanks. Okay. This is actually should be four cases here because this is I less than J. And so we should have the case if C of I is equal to A, then C of J is equal to U, and so on. That's what I mean by and conversely. And that's the same thing as saying these are the permitted matchings. So that's one condition. A second condition, I wouldn't have put it in here, but the book does. And it's realistic biologically, but algorithmically it's just annoying. I has got to be less than J minus 4. It's just annoying. All that means is you can't match with a character that's too close to you. You have to have at least 4 characters between you. And we had that here. If you look at all the matchings that I have, this looks like the closest one, and it has 1, 2, 3, 4 characters between it. Okay? Algorithmically, that doesn't really, if I took it out, it would still be an interesting question, still an interesting problem. But, okay, but for biological reality, he has it in there. 3 is the most interesting one, which is the non-nesting. Okay? Is the nesting, the non-intersecting. And how do I write that mathematically? If Ij and I prime, J prime are matched, then I less than I prime less than J prime is impossible. We don't permit this kind of matching of pairs. Let's just look visually what this looks like. I prime, J prime. If you match I to J and I prime to J prime, then you have the intersection. Okay? So this is saying if you ever have these two kinds of pairs, two pairs in your matching, then you cannot have this kind of interleaving, because then you'd have the intersection of the matched pairs. So, and one more thing. And I know that I'm doing this in a different order that's in the book. I know that in the book this is the last condition. But anyway, the fourth condition is that a character, a position, can only be in one matched pair. Okay? And you see that in here. Every character is either, in a particular position, it's either not involved in a matched pair at all, or it's involved in only one matched pair. Okay? You don't have this C, for example, matching with, well, this C is matched over here with just G. It's not also matched with this G. Okay? So every position is in one matched pair only, at most. Can be in one matched pair at most. Okay. A set of a set of pairs that satisfies this, all these conditions, is called a secondary structure. Okay? So a secondary structure is a set of matched pairs that satisfies all of these conditions. This is a secondary structure because it's it represents a secondary structure because it satisfies all of those conditions. If I had this extra pair in there that I just erased, that would not be, then what we're looking at would not be a secondary structure because it would violate the non-intersecting condition. Okay, and so our problem now is, given an RNA sequence, find a secondary structure that maximizes the number of pairs, matched pairs that are in that secondary structure. And the reason for maximization is that each pair that's in the secondary structure, that represents an actual bond that's happening there. And the more pairs you have in here, the more stable this folding is. And so it's believed that to first order of approximation, a reasonable guess for what the secondary structure of the molecule is comes from finding the pairings in here, the secondary structure that has the most bonded pairs. Okay, so it's the most stable and therefore the most realistic. Okay, I've only defined the problem now, and I haven't even written it down, but I just said find a secondary structure that maximizes the number of pairs. Now, how are we going to solve it? Well, we have three techniques that we've learned: divide and conquer, greedy algorithm, or dynamic programming. Okay, well, divide and conquer, you could think of all kinds of ways. I'm not going to, but just think about greedily. Well, you've got an A, it's supposed to match with U's. Can't be too close, so maybe we'll go up and match it with that U, the closest one, or match it with the farthest one or something. You can think of some greedy algorithm, and you hopefully could quickly convince yourself that that won't find the maximum. So if divide and conquer sounds too complicated at this point, greedy won't work, what do we have left? Dynamic programming, yeah. So next time I'll show you the dynamic programming solution to this.